Because I just made up with all the beta alumni, so like they're all these weird 50-year-old men, like 50-year-old men playing beer pong, getting really drunk, and like this is weird. It's their
I think is it on the
I know, and I was like,
because I think I have like
yeah.
But yeah,
I know it's a weird thing. They're like old women.
you just
I know you want to. Please good for yourself.
but
It was really weird.
that's because I know I need to get started writing because I don't want to do it for free. But then of course,
Okay, guys, here's a bit of a look ahead. We are going to wrap up chapter 14 this week, and it's a lot, but you've got 4 days to get your minds right. And then the stuff that you're doing this week will not be due until Wednesday, because you won't be here on Monday. And on that Wednesday, we'll do a review, sort of group work and synthesis, and then Friday we'll have an exam just over chapter 14. Okay, very similar kinds of problems to what you experienced on the last exam. Any questions about this? All right, today we're going to try to cover 2 sections. The large majority of my time will be spent on section 14.5. 14.6 is really tiny, and I'm just going to mostly point at a few things and let you read. Literally, I think it's that long in the book. And you've got a few problems there to do. Before I get into today's work, though, are there any questions on web work or any homework? Sorry about the mass confusion last night. I was a little bit, I don't know what. Anyway, we're all over it now, though. Questions? Yeah?
So for the second sub problem, the method in the book talks about taking partial derivatives for each component.
Yep.
How do you evaluate for Z?
So that's kind of the, let me pull that up here. Right here, I guess. Really? How about this? No? There we go. And that. And this. All right. So, oh, not in this section, right? The prior section? Got it. Oh my God. There we go. Am I really suffering? Yes, I am suffering. Okay. I don't know why. It doesn't want to go, or I'm just not thinking about it correctly. Almost there. Yay. 12 or 9? 12. Find an equation for the line normal to this guy at 2, 1, 4. I didn't go through the derivation, but the idea here is whenever you can write a surface as z equals something, which you can in this case, right? Z equals 1/2 x squared plus 2y squared. That's what you have to do in order to use that formula. Okay, if you can write it as z equals something, then the normal derivative, or sorry, the normal to the surface can be written f sub x, f sub y, -1. And this is only if you can solve for z equals f of x, y. Okay? Yep. And in that special case, then the normal is fx, fy, -1. What we're going to do, in fact, a little bit today, we're going to generalize this notion to where it's not fx, fy, -1, but in fact fx, fy, fz in the third slot. Okay. Other questions? Yes.
So I think I missed the email saying that actually do 12 until like this morning when I had already done 9.
Yep.
Should I just turn that
Oh,
in?
yeah.
Okay.
Other questions? Did everybody get the box except Rachel? Yep, I guess so. You can just get off your butt. Oh, there's one other person. Okay, it's worth it now. Okay. Today we get into the directional derivative. And we'll introduce something called the gradient operator, which will be your friend throughout the remainder of the semester. Okay, the scenario that I want you to start imagining in your head is one that we've talked about before. You go out and you're on some hilly terrain, and you're standing at some location which we'll call X naught, Y naught. And the steepness of the terrain that I'm about to encounter depends on the direction that I'm going to go. Right? Okay. And that's fundamentally different from Calc 1, where when I'm standing on the curve, there are only 2 ways for me to go. This way, or 180 degrees that way along the curve. And so the slope of the curve really was just one thing, right? I mean, it was just the slope of the curve right where I stood. And maybe if I stood over here on the curve, it was a little bit different. But I didn't have a whole lot of choice in what direction I was going to walk. But now we're talking about surfaces, and we've opened up the possibilities with regard to slope. So now I'm standing on the surface, and the slope in this direction is a little bit different than this direction, is a little bit different from this direction. And what we have to do is quantify that. And the tool that we're going to use is something called the directional derivative. So imagine you're in the XY plane, and you're at some point of interest, say X naught, Y naught. Okay, you're in the XY plane, and that's something that you have to remember. I'm going to be talking about being on the surface and walking in particular directions. What I really mean is I'm on the XY plane, and the surface is above me. And if I'm on the XY plane and I walk this way, what's the surface above me doing? Is it going down? Is it going up? How steep is it going down? How steep is it going up? So I'm going to be talking about that. And right, there are a lot of different directions I could go. And what we're trying to understand is the slope of the surface in different directions. Nope, can't write. Okay. All right, let me motivate this a little bit. What we're going to be interested in is a direction. So you're going to be given a direction, U, and a location, X naught, Y naught. And this is kind of in the XY plane. So we're going to be given a direction, U, and a location, X naught, Y naught. And what we want to know is how the surface is going to change, or what's the slope of the surface in that direction. This is very different from Calc 1. Okay, let me motivate this a little bit, and let's talk about the partial of f with respect to x and the partial of f with respect to y are examples of directional derivatives. Okay? How are they examples of directional derivatives? In the sense that you've already looked at this, right? The partial of f with respect to x describes the slope of the surface in what direction? Exactly. And the partial of f with respect to y is the slope parallel to the y-axis. Obviously, there are more than just those two directions, right? There are a whole infinity of directions, all the different possibilities of directions that I could go. But these are examples of directional derivatives. If you look at the partial of f with respect to x at this location x naught, y naught, okay, what we're really looking at is the slope in this direction, right? If you use the limit definition, and this is something I didn't talk about in class, but it's in the book. If you use the limit definition of this quantity, it's, hold on to your hats here, it can be written like that as a difference quotient. There's a lot going on here. So all I'm interested in is the partial derivative of f with respect to x. So that's in the first slot. So in the first slot, what I do, here's kind of an x plus delta x, and here's an x over delta x. Everything else is constant, just goes along for the ride. So one way that I could write this partial derivative is like this. And I know that's a plus sign and that's a t. Okay. So it's x naught plus t comma y naught, x naught comma y naught. Okay? All right. So that would give me the partial of f with respect to x. Let's generalize this. And now you really have to hold on to your hats. Let's generalize this. I'm going to call this capital D sub u. Let me define u here for you. u1, u2 of f at x naught, y naught. So there's a lot going on here. I'm taking the derivative of f at x naught, y naught in the direction u. So I've specified a location and a direction in which I'm interested. Those two things have to be specified in advance. All right. So generalizing this difference quotient, I get something that looks like that. All right. So this difference quotient represents going to x naught along the x-axis, parallel to the x-axis. What this difference quotient represents is going to the point x naught, y naught along the direction u1, u2. So this is a generalization of this. And here's why we learned the chain rule last Friday. That's the same as taking the derivative with respect to t of this function and evaluating it at t equals 0. All right, let's watch that. So the chain rule says if I want to take the derivative of this thing with respect to t, I take the partial of f with respect to this slot times the derivative of this slot with respect to time, plus the partial of f with respect to this slot times the derivative of this slot with respect to time. So that's f sub x times dx dt plus f sub y times dy dt. And all of that, again, is going to be evaluated at t equals 0. Let's fill in the pieces here. What is the derivative of this slot with respect to t? u1, right? u1. And the derivative of this slot with respect to t is u2. Another thing that's important to know is what happens when I plug t equals 0 into this? What does it turn into? X naught. And this guy? Why not? So I'm going to do all of that. And I now have this funny symbol on the left-hand side is actually the partial of f with respect to x at the point times u1 plus the partial of f with respect to y at the point times u2. And I'm going to write this in a slightly suggestive fashion. I'm going to use the dot product notation. This is really the dot product of this vector with the original vector u. And we're almost there. We're going to define, as mathematicians are wont to do, we're going to define the gradient of f to be this vector. Okay, and if we make that definition, then we can write the gradient of f dotted with the vector u. And what we've done is we've hidden a whole mess of mathematics into a very compressed box of symbols, which is, again, what mathematicians have a tendency to do, right? We tend to take lots and lots of stuff and compress them into very dense symbols. And it's up to you guys to figure out what these symbols mean and how to use them and internalize them. So before you got to class today, an upside down triangle next to an F meant nothing to you. Now it means this much to you. And by the end of the semester, it should mean this much to you. Right? So what we've done is we've started loading this symbol with meaning. And at the moment, it's got the very barest meaning. This symbol next to an F means this vector, the partial of f with respect to x, comma, the partial of f with respect to y. It's that vector, whatever that means. And my hope is that by the end of the period, I'll be able to load even more information into this symbol and show you how useful it is. Let me just generalize this symbol. This generalizes to more than one or to more than two variables. So the gradient of f of x, y, and z is just f sub x, comma, f sub y, comma, f sub z. All right, so as many variables as you want. If you have n variables, then the gradient is a vector with n components, and each component is just the partial with respect to that variable. Okay, and it can go out as long as you want. We're only going to work with 2 and 3 variable functions. 2 and 3 variable functions. All right. This thing is called the directional derivative. And there's one more little caveat that I have to add to this collection of symbols. Compare these two difference quotients right here. What's U1 and U2 up here? What's U1? U1 is 1, U2 is 0. So what's the vector U? 1, 0. And that vector is parallel to the x-axis, right? So that sort of makes geometric sense. Another important thing here with this directional derivative is we want direction but not magnitude. So we normalize, meaning we make u a unit vector. All right, the directional derivative in the direction u, you have to be using a unit vector. have to use a unit vector. Why? There are reasons later that we'll talk about, but it mostly has to do with if you leave the magnitude in there, it's going to mess up the rate of change. It's not going to give you the right rate of change when you do the directional derivative. That magnitude is going to interfere with this value that we're interested in. And so you take it out. And the way to take it out, does anybody know how to get a unit vector from an existing vector? You remember how to do that? Divide by the magnitude. So if I ask for the directional derivative in the direction of the vector, say 2, 3, the first thing you're going to do is take that vector 2, 3 and compute its length, which is what, 4 plus 9, root 13, right? And you're just going to divide both components by root 13, and you're going to work with that vector. Okay? And if you forget to do that, what's going to happen is your directions are going to be correct when you're doing things, but your absolute values, your magnitudes are going to be wrong. And so just normalize right off the bat. All right.
Could you potentially wait till the end to normalize it?
Yes, but there are times when what's going to happen is u is actually not going to be a constant vector, it's going to be a variable vector. And then what you want to do is, even then though, you could probably still normalize it at the end. So yeah, as long as you remember to do that. Yeah. All right. Let's compute one of these things, and then we'll talk about the more interesting aspects of this, which is the geometry. So I'm interested in exercise 14.5.1. I wish this thing would work, but apparently it's not going to. There we go. It's always good to start with exercise 1. Find the directional derivative of f, where f is this function, in the direction 2u at the point 1, 1. There's a lot of stuff there that you're being given. But you can see, hopefully, that you need all of that information, right? F describes the surface that you're interested in. The point 1, 1, you go to the particular place on the xy plane that you're interested in. There's the surface up there. You don't really know what it's doing. And then the direction 2, 1, you sort of move around until you get to the direction 2, 1, and you look up at the surface and you ask yourself, how is it changing up there? And that's what the directional derivative gives you. So you need all of these sort of prerequisite pieces in order to even formulate the question. Where are you interested in this derivative? And in what direction are you interested in this derivative? Okay, so that's x squared plus xy plus y squared. Try to remember that. And the location, I think, was 1, 1. And the direction was 2, 1. And you're asked to find the directional derivative in the direction u of f at 1, 1. Okay, remember what the first step is. Normalize. So that means u is actually equal to 2, 1 divided by root 5. And so u1 is 2 over root 5. u2 is 1 over root 5. Okay? Everybody see what I did there? Good. The other thing I need is the gradient. Okay, the gradient of f is the vector of first partial derivatives. Okay, so we need f sub x, which in this case is 2x plus y, and we need f sub y, which in this case is 2y plus x. So everybody see that those are the partial derivatives. Now, I'm not interested in the partial derivatives everywhere. I'm only interested in them at this location, 1, 1. Just so happens that they're the same here, but that's not generically the case. So to find the directional derivative, I take this gradient vector at 1, 1, which is 3, 3, again, just sort of an accident, and I dot it with u. And let's see, that's 6 over root 5 plus 3 over root 5 is 9 over root 5. Okay, so the directional derivative of this function f at the location 1, 1 in the direction 2, 1 is 9 over root 5. My God, what does that mean? Okay, so I go to 1, 1 again. I point myself in the direction 2, 1, and I look up at the surface. Is it rising or falling? Why? Because it's positive. Is it rising particularly quickly? I don't know. Depends on what you think is particularly quickly. But 9 over root 5, yeah, it's certainly more than 1. It's rising faster than, say, the line y equals x. Okay? So you get an idea of what it's doing as I look in this direction. What happens if I turn around 180 degrees and look in that direction? What do you think's happening? It's going down, right? What would the u be in that situation? Yeah, it would be not negative 2, 1. It would be just the negative of that vector, right? It would be negative 2 over root 5, negative 1 over root 5, right? That points me 180 degrees in the opposite direction. What happens to that minus sign? If there's a negative sign here and a negative sign here, what happens to this guy? It becomes negative, which is exactly what you would hope, right? So I'm standing here, I'm looking in the direction, I know it's going uphill. I turn around 180 degrees, I know it's going downhill, so I expect the derivative to be negative. And that's exactly what I get. Yeah?
Is that 9 over root 5 just slope the tangent line at that point?
Yeah, pretty much. Yep. Okay. Questions about that calculation? All right, that's really mechanical. I expect you to be able to do that right now. Okay, find u, normalize it, find the gradient, plug in the point, dot product, done. I also expect you to understand what it means in terms of the geometry of the surface. Okay, so if you look at some of these exercises, 1, 2, and 3 are all similar kinds of things. What I'm interested in now is less about this calculation. Although the calculation is important, you have to be able to do it. I'm really interested in the geometry. There's a very deep geometric significance to this object right here, the gradient of f. And that's where we want to go next. Okay, so recall that the directional derivative in the direction u of the function f at the point x naught, y naught, I know, it's crazy, isn't it? Is the gradient of f at x naught, y naught, dotted with this normal vector u. Do you remember what the cosine identity for the dot product says? So in terms of these quantities, I get that, right? And I'm suppressing this x naught, y naught thing, but we secretly know that this is being evaluated at this point, x naught, y naught. What about this right here? 1, because it's a unit vector. Okay, so what we're left with is, all right, what I want you to do is I want you to connect these two guys, and I want you to think about I want you to think about a fixed f and a fixed location and a varying u. So here I come back to this location underneath the surface. The surface is up there, it's the same surface. The location is fixed. And what I'm interested in is in which direction is the surface steepest? That's the question I want to ask. And unless it's a plane, well, even if it is a plane, unless it's a flat plane, a horizontal plane, there's going to be an answer to this question. There's going to be some direction which is steepest. Does everybody buy that? Okay, so the question is, what is that direction? What is the direction that I should travel for the steepest?
Well, if your gradient is all non-decimal, like all grade 1 or greater, then shouldn't it be where cosine theta equals 1?
In fact, it doesn't matter about the gradient, right? The gradient at this point, at this fixed point, is what it is. How do I get the most bang for my buck? I line up u with the gradient. Okay, so the gradient is pointing in some direction, right? The gradient is a vector, as I pointed out earlier. Right here, the gradient is a vector. You plug in the value, whatever your location is. This is now some vector, a fixed direction in space. I will maximize the dot product if u lines up with that direction. So the directional derivative is maximized if u is parallel to the gradient of f. And I'm using the word maximized a little bit loosely here. Right, so I come to the point, and the gradient vector is, say, pointing in that direction. So I know, based on this cosine identity, that that's the steepest direction that I can go. And if I turn around 180 degrees, I know that that's the quickest descent that I can go. So that's the direction of steepest descent. That's the direction of steepest ascent. Okay? And so when I say it's maximized in the direction parallel, what I mean is either you're climbing as quickly as you can, where u is pointing in the same direction as the gradient, or you're falling as quickly as you can, where u is pointing in the opposite direction. But in either case, when u is parallel, that's the most extreme direction. That's the most rapid change that you can experience. Yes?
So does that mean that the gradient of f is pretty much defined as the steepest?
You can define the gradient that way. The way we're defining the gradient is as f sub x, f sub y, f sub z. But there are textbooks and there are treatments where you would define the gradient to be the direction of steepest ascent, and then everything flows from that. It's just a different approach, but that's not the one that we're gonna follow. Okay, so this happens when theta is equal to 0, same direction. and this is the steepest descent. Bless you. Or when theta is equal to pi, and that's the opposite direction, and that's the steepest descent. All right, we've learned a lot about the geometry of the gradient vector. We've learned that for some strange reason this thing points in the steepest direction. Frankly, I'm not even super interested in that, although there are some applications where that's important. There are some numerical methods, for example, Newton's method, that relies on this idea, Newton's method in higher dimensions, that rely on this idea. But what I'm interested in is there's another interesting value of theta in this situation. What is it? There's a value of theta between theta equals 0 and theta equals pi that might be interesting. Pi over 2, right? What happens at pi over 2? Yeah, so when what does that mean geometrically? So here I am, standing on the surface, I'm pointing in the direction of steepest ascent. Or I turn around and I'm pointing in the direction of steepest descent. If I go 90 degrees,
That's like parallel to the x-axis.
not necessarily the x-axis.
Parallel to the xy plane.
Yeah, although all these directions are in the xy plane, so that's not really. The directional derivative is 0 in this direction. So that means if I walk a little bit in this direction, do I rise or do I fall? I do neither. So if I go this direction, I go up as quickly as I can. If I go this direction, I go down as quickly as I can. If I go right angles to that direction, I go neither up nor down. Let's pretend I walk a little bit in that direction, and I do the gradient again, and I go 90 degrees to that, which is 0, and I go a little bit, I neither rise nor fall. Now I do a new one, and I go perpendicular to that, and a new one. What am I following? I'm neither rising nor falling. I'm following a level curve. This is the really deep geometric significance of the gradient. So if I follow this condition, two ways to look at this. I can use this information to follow a level set, or I can just note the gradient vector is perpendicular to this level set. Right? Here's the direction of steepest ascent. If I go 90 degrees, I know that I'm going to be following a level curve. Well, don't bother going 90 degrees. Just keep facing the steepest ascent and note that the level curve hits this point right here perpendicular. So here's the direction of steepest ascent. The level curve going through here is perpendicular. The gradient is perpendicular to level sets. Okay. Definitely the big takeaway is that statement right there. Let me try to, I know that I've thrown a lot at you. Let me try to give you an example that maybe will help you visualize this. So let's pretend that I take Ryan's backpack, I stick it in the corner, and I light it on fire. Okay? And we get it going really good, and you know it's really roaring now. That's the origin now of our coordinate system. And we let it go for 10 minutes or so, and it's nice and toasty over here. Everybody kind of has an intuitive idea of how temperature and heat flow works. You're going to sort of get into a stable equilibrium in the room as long as the backpack keeps burning. So that when I'm near the backpack, it's hot, and when I'm over there where Nick is, it's cool-ish, relatively speaking, right? And the temperature is going to decline steadily as I go from the origin over to Nick. So imagine there's some function, a temperature function, in the room at a moment in time that describes the temperatures in the room as a result of this burning backpack. Maybe you're close to the backpack and it's 120, 130 degrees, really warm. And maybe by the time you get here, it's only 90 degrees. And then you get over there and it's more like 70 degrees or something, like ambient temperature, not really affected by the fire. What I want you to do now that we have this picture in our head, this thought experiment going, is I want you to imagine the set of points in space where the temperature is 80 degrees. What does that set of points look like? It's part of a sphere, right? And if the burning backpack were just suspended in space, in fact, it would be a perfect sphere right around the center of that backpack. Does everybody see that? And if I move out a little bit, 70 degrees, that's some other sphere, right? All of the points in space where the temperature is 70 degrees is a sphere as well. And in fact, every point in space has a temperature, and every point in space has a set of peers, if you will, who all have that same temperature. And that set of peers always forms a sphere. And it doesn't matter. The only thing that really matters is what's the relationship between the sphere, the size of that sphere, and the temperature.
The size of the sphere increases as the temperature decreases.
Right, so the lower the temperature, the bigger the sphere, right? So there's a tiny sphere down there, which is essentially, 150 degrees or whatever, and then there's a really big sphere out there by Nick where it's 70 degrees. Everybody got that picture in their head? Okay, let's try to do a little bit of math related to that example. So, wow, this is just struggling here. Maybe here. Yeah, there we go. And here. And here. Okay, so we have the burning backpack. Okay. Burning backpack. And we have these shells. Okay, and the shells are maybe 150 degrees, 120 degrees, and maybe 90 degrees. And it's not just those shells, right? There's 150.000001 degrees, right? Every value that you can think of has a shell associated with it, has this level set associated with it. And every one of those level sets looks like a sphere. All right. Let's make up a temperature function. Let's call it phi. And we'll say that it's some constant divided by x squared plus y squared plus z squared. Why did I choose that expression as my temperature function?
Equation sphere, or contains any of the equation sphere.
Right. your temperature in the room depends on your distance from the origin, right? Go ahead, Hannah. What were you going to say?
Well, I guess the bottom is basically the distance formula of like any point on a sphere.
To the origin.
So it's the length of the sphere times a constant, however much temperature it is.
Right, however I want to adjust it. So does everybody see that? The further away I get from the burning backpack, the smaller this number gets. And K is just some constant that makes the numbers work out correctly. There is a problem with this model. What's the problem with this model?
Change of density due to heat, or is that what you're talking about?
Meh.
You're talking to purpose.
You're gonna have a zone, I guess, like absolute zero. Is that what you call it?
Actually, it'll approach zero, yeah. So that's not terrible.
Well, that's a pretty linear relationship. It might not actually decrease.
Yeah, so the question is it really like 1 over r, or is it 1 over r squared? It's actually 1 over r squared, but I didn't want to deal with that. Okay. Yeah, the center of the fire. So this model breaks down at the origin, right? It's not infinite temperature at the origin. So what you would do here is you would say this model holds, as long as you're, say, more than 5 feet from the backpack, this model holds. All right, so we're not going to worry about that. What I am interested in is, can we show that the level sets are spheres? Can we do that? Well, how am I defining level sets in this burning backpack situation? What do I mean? How do you get to be a member of a particular level set? You're a specific temperature, right? So the level set associated with, say, 120 degrees is all of those points where phi is equal to 120 degrees. Agreed? Let's see what that looks like algebraically. Well, that's the same as setting k over the square root of x squared plus y squared plus z squared equals to 120 degrees. Okay. So what do you recognize there? So I isolated this x squared plus y squared plus z squared and moved it over to the left-hand side, divided both sides by 120, then I squared both sides. And what am I left with?
Equation of sphere.
This is the equation of a sphere. Better yet, we actually now we even know what the radius of a particular level set is. The radius is k over 120 in this case, or k over whatever the temperature is that you're interested. But it's certainly a sphere. So yeah, we can show that these level sets are spheres. All right, our observation about the gradient then says that the gradient of phi is perpendicular the gradient of phi is perpendicular to level sets. Well, let's see what the gradient of phi is. The gradient of phi is the partial of phi with respect to x, comma, the partial of phi with respect to y, etc. And I'll just do this out and I'll explain it in a sec. And I'm even going to go one step further, and I'm going to pull out this common factor. I'm going to leave the minus sign in, actually. Okay. First of all, let's talk about the partial of phi with respect to x. So I'm going to take this k over root x squared plus y squared plus z squared. I'm going to write it as k times the quantity x squared plus y squared plus z squared raised to the minus 1/2. Right? That way I can differentiate it. I bring the minus 1/2 down. What's left behind is the is x squared plus y squared plus z squared raised to the minus 3/2, right? Times what? The derivative of the inside with respect to x, which is 2x. The 2x, the 2 from the 2x hits the 1/2 from that derivative, and they cancel each other. And all that's left behind is a minus x. And then that minus x is over top of this, minus y minus z. In fact, because of the great symmetry of this formula, the partial of x, partial of y, partial with respect to z, they all look basically the same. You just change the x to a y, the y to a z. Does everybody see that? How to compute that gradient? Good. Okay, let's talk about the geometry of this result. I'm not terribly interested in the scalar out front, other than that it's positive. And what I'm interested in is, here's the burning backpack. Here's a point in space, x, y, z. Which way is the gradient pointing at this point, x, y, z? It's pointing towards negative x, negative y, negative z. That's this direction, towards the origin. Why? Well, if I go to the origin here, and I go minus x, minus y, minus z, I'm actually back down through the wall, right? In the exact opposite direction as x, y, z. So the vector minus x, minus y, minus z is pointing, has its tail at the origin, and is pointing that way. And the point x, y, z is over there. Now take that vector, minus x, minus y, minus z, drag it over here, because remember, vectors don't have location. Put its tail right here. Where is it pointing? It's pointing straight at the origin. Is that the direction of maximum change of temperature? It is, because if I go that way, I'm headed straight towards the burning backpack. What happens if I change the sign on this vector? Now it's pointing this direction, right? That's the direction of maximum decrease, maximum descent, directly away from the backpack. All right, one last question. Where's the level set for this point? What is it? It's a sphere, right? This vector, normal to a sphere around the origin? Yeah. Same with this guy. 90 degrees? Tangent to the level set, right? Okay. That's generically true. Doesn't matter that it's a nice, lovely sphere. Any surface, if it's the level set of some function, then the gradient is perpendicular to that surface. Questions about that? All right, let me, again, there's a lot going on here. You've got to go home, you've got to read it, you've got to think about it, but let's do an example. The example, let's see, that I want to do, let's just pull one from the book here. How about something like 11? Find an equation for the plane tangent to this guy at the point 113. To find a tangent plane, what do I need? To find any plane, what do I need?
A normal vector.
Normal vector
And a point.
and a point. I've got the point. I hope I have the point. You plug in 113, hopefully you get 7. I need a normal vector. And now you already have methods at your disposal for finding the normal vector. For example, you could try to solve for z and then use the method that I talked about at the beginning of class. But you can see that solving for z here is going to be a little bit of a pain. It's going to introduce a square root, which could get messy. And there's always the problem of when you introduce that square root, you get the plus or minus, and you don't really know which piece you're dealing with. Which, should I use the plus square root or should I use the minus square root? And rather than worry your head about that sort of stuff, let's just use this new tool that we have. And so what I'm going to do is I'm going to look at x squared minus 3y squared plus z squared. I already forgot it. I have a short-term memory issue here. Minus 3y squared plus z. Okay, this, thank you. This is a level curve, or a level set, I should say. This is a level set of the function so this surface that I'm interested in just happens to be a level set of this function. Why is that? Well, which level set is it? It's the one corresponding to the value 7. So if I set this function equal to 7, that's a level set of that function, right? And in fact, it happens to correspond to the surface that we just so happen to be interested in. What's useful about this observation is we now know that the gradient of f is perpendicular the gradient of f is perpendicular to level sets of f. And this thing that we're interested in just so happens to be a level set of this function f. It's not an accident, right? I basically took this thing and built my f out of it. Okay, well, let's find the gradient of this guy. Remember that the gradient of f, when you have 3 variables, is f sub x, comma f sub y, comma f sub z. So let's get those 3 derivatives in place. So now, we're not interested in this guy quite yet. We're interested in this guy. The partial of that guy with respect to x is just 2x. With respect to y and with respect to z, okay? Now, this is the gradient function for just some generic point in space. What I'm really interested in is what's the gradient vector at a particular point in space. What's that particular point? 1, 1, 3. All right, 1, 1, 3, so that's 2, -6, and 6. Now, how do we interpret this? All right, there's this guy is on this surface. This surface is a level set of this function. This vector is normal, then, to the surface at this point. All right, let's go back and look at the question. Find an equation for the plane tangent to this surface at 1, 1, 3. I've got a normal vector. I've got a point. I'm done. And I guess technically that's not a vector, but a point. And so I'll just write 2 times x minus 1 plus six times y minus 1 plus 6 times z minus 3 equals 0. That's the equation of the tangent plane. you've done this before, but again, the gradient let us avoid solving for z. But if you wanted to, you could solve for z and you could use the formula that was in the previous section. Questions about that? So there's going to be a whole sort of collection of variations on this theme. You've got tangent planes, you've got normal lines. Okay? Essentially asking the same question. The only difference here is for the normal line, you find that normal vector in that point, and instead of building a plane, you build a line, right? Okay, so you just got to be careful of how you read. There are more interesting ones. I thought there were more interesting ones. 7 is pretty crazy. 8 is pretty crazy. Let me give you one more example of, so you've just got to think about the geometry of these things and try to build these mathematical representations. Let me talk about another kind of problem I think that you'll see in web work. Let's pretend you've got a plane out here. And you've got a sphere. In the book, I think the book does an example like this. So, imagine this plane sitting out there. Can you find the two points on the sphere where the tangent planes are parallel to this given plane? There's one there, and there's one back here. So there's a point here where the normal vector is parallel, and there's one back here where the normal vector is parallel. So you can answer questions like that. There's an exercise in the book that goes through that kind of thing. I think for the sake of time, what I'm going to do is jump to the next section, which is higher order derivatives, and I don't think it'll take very long, and we'll get out of here. Any questions about the gradients? All right. So higher order derivatives, as I mentioned, this is a really short section. I think I can get it on almost all on there in one page. It starts here and it ends here. Okay. We kind of foreshadowed this in an earlier exercise. We know about the first partial derivatives, f sub x, f sub y. This is really just what do second derivatives look like? What do third derivatives look like? For example, f sub xx. You start with the function, you take the partial with respect to x. Whatever comes out of that, take the partial with respect to x. You've got f sub xx, the second partial of f with respect to x. These mixed partials, again, we talked about those. Take the derivative with respect to x and then with respect to y. Or the derivative with respect to y and then with respect to x. And then there's finally fyy. So for example, this function f nominally has 4 second derivatives. xx, xy, yx, yy. What if it was a function of, say, 3 variables, x, y, and z? How many first partials would it have? First partials? 3. How many second partials?
9.
I hear 9. 9?
Some of them are equal, right?
Well, yeah, but let's not get into equal yet. Right? You've got how many different ways can you take those two derivatives? Well, you've got 3 possibilities in the first slot, right, and 3 possibilities in the second slot. So how many total ways can you take the second derivative? 3 times 3, or 9. Okay? But yeah, as Andy points out, it gets a little more complicated than that. If I ask you how many unique second derivatives there are, it gets a little dicier because of Clairaut's theorem. Clairaut's theorem points out to us that, in fact, mixed partials are equal. So f sub xy is the same as f sub yx. And so if you take that information and you go back up to, say, example 14.22, there are really only 3 unique second derivatives. So nominally there are 4, but by Clairaut's theorem, the mixed partials are equal. And so, okay. And that's actually true in higher order. Go ahead.
So if there are 3 variables, does it have to be, do the mixed derivatives have to contain all 3 variables, or can it be x, y, y, x, x, y?
Right, so it gets very complicated, not complicated, it's actually dramatically reduces the number of derivatives, but counting how many there are is complicated. It's something that you'd want to do in like a combinatorics class or something. But yes, for example, for a function of 3 variables, f sub x y and f sub y x are equal. F sub x z and f sub z x are equal. F sub y z and f sub z y are equal. So we've blown away already gotten rid of 3 of the second derivatives. Okay? It's not the case, for example, that f sub xx is the same as f sub zz. Those are different, right? But whenever you have mixed ones, you can shuffle them around without changing anything.
So I guess my question is, do the mixed partials have to be partials of the same variables in order to be equal?
Give me an example.
If you have the xz, f of xz, is that the same as f of xy?
No.
Okay, all right.
Right. So that's generally not the case. But f sub x z is the same as f sub z x z is the same as f sub z z x.
So order doesn't matter.
Order doesn't matter is what this is saying. Yes. Yes. Same variables, same number of times, equal. Okay, that's what Clairaut's theorem says in general. So order doesn't matter. Really remarkable result. Okay, and the exercises at the end of that section are pretty straightforward, just computing a few first and second derivatives, and web work is more of the same. So any questions before I turn you loose? All right, I'll see you Wednesday.